So good morning, everybody, and welcome to another wonderful day of 317. Today, we're going to finish our discussion on applications of Bernoulli's equation and energy balances, and hopefully start delving into momentum balances. So from last time, we were looking at an application of Bernoulli's that involved tank draining, and by defining our points of our energy balance as the top of the tank and the bottom of the tank, we could develop a simplified Bernoulli balance. And what we arrive at when we're wanting to quantify the discharge velocity, we find that in order to quantify that, all we really need to know is the height of the fluid and gravity. Now, I also mentioned that due to the nature of the geometry and how the fluid flowed due to momentum, the actual flow area contracts as a function of that orifice geometry, such that we have to add an additional correction factor known as a discharge coefficient or a coefficient of contraction to correct for that phenomenon. With those coefficient of contraction typically falling within a realm of somewhere between 0.6 to 0.98, depending on the nature of the actual outlet involved. Now, we started working at the end of class last week, looking at calculating some information following the first example in this lecture set, trying to identify the initial flow rate of the water, as well as how long it would take to drain the water. And so we left off looking at this system and trying to redefine a mass balance for this system. So that's where we will pick up today. And so by looking at this tank, I can define our system as the tank and the water in it, such that if I looked at my mass balance, I can say, well, I have mass in minus mass out plus mass generated minus mass consumed equals mass accumulated. Now, which values in this balance can I eliminate? What do you guys think?
Generated, consumed, and probably accumulated.
So I can get rid of mass generated and consumed. I don't have any reactions. I actually can't get rid of mass accumulated. Now, my next question would be, do I have mass coming into the tank? I don't. Do I have mass leaving the tank? I do. So that tells me my balance is simply mass out equals mass accumulated, or I would probably just write it like this: mass out equals negative mass accumulated. That lets me know I have a negative accumulation in my tank because I'm losing material over time. So I need to create relationships for mass out and the mass accumulation in the tank. Well, in this system, my mass out would simply be the density times the volume out, which we defined last week as the area of the outlet or the orifice times the discharge coefficient times the square root of 2 times gravity times the height of the fluid. Now, the trickier part comes when I'm defining my accumulation term in terms of how do I quantify the negative accumulation that's happening in the tank. Well, it's simply a mass flow rate. So I have a density times some form of volumetric flow rate, Where in this case, I'm looking at the area of the tank as well as a pseudo velocity, or the change in the fluid height with respect to time. So if I do that, I can set up an expression that looks like this: negative density times the area of the tank times the change in height with respect to time equals the density times the area of the orifice or the outlet times the discharge coefficient times the square root of 2 times gravity times height. Now what I can do for this, since density appears on both sides, I can eliminate it, and I can do a separation of variables. So in this case, what I would do is, since I have a height under a square root, I would probably put that by itself, or I'd end up with a negative delta dH over the square root of h equals the area of the outlet over the area of the tank times the discharge coefficient times the square root of 2 times gravity times delta t. So if I can integrate this from my initial height to my final height, and then I integrate the other side from time equals 0 to time equals some time t that we're looking for. If I do this integration, what I should be left with is negative 2 times the square root of h evaluated at the initial height and the final height, which equals area of the outlet over area of the tank times the discharge coefficient times 2 times gravity times time, evaluated from 0 to t. So if I put in the values, I'm left with a negative 2 times the square root of the final height minus square root of the initial height equals a naught over a sub t times the discharge coefficient square root of 2g, and then there's simply t. Now, if I distribute the negative,
where do you get that negative 2 from?
The negative 2, the 2 comes from evaluating the integral 1 over the square root of h, because it's h to the negative 1/2.
Got it.
So I can distribute the negative, and what I can do is essentially rearrange that subtraction. And then for the last step, I would put time by itself, because that's the variable I'd like to solve for. And so I can say time equals the area of the tank over the area of the outlet times the square root of 2 over g. Now the square root comes on the top, because if I divide 2 divided by the square root of 2, I'm left with the square root of 2. And then I get times 1 over the discharge coefficient times the square root of the initial height minus the square root of the final height. And this is my expression to solve for the time to drain the tank from a certain initial height to a certain final height. Where for this problem, my initial height would be 10 feet, my final height would be approximately 0. So plugging this in, actually one thing I would note is, since area is simply pi times d squared over 4, you can also write it as a function of the square of the diameters, because the pi and the 4 show up on both the numerator and the denominator of this expression. So you get with an expression that looks like this: diameter of the tank squared over diameter of the outlet squared times the square root of 2 over gravity times 1 over the discharge coefficient times the square root of the initial height minus the square root of the final height. So plugging this in, I get 10 feet squared over 4 over 12 feet squared, because the outlet diameter was 4 inches times 2 over 32.2 feet per second squared, times 1 over the discharge coefficient, which for this system was 0.7, times the square root of 10 feet minus 0. Which I believe, if you do the math, you get something on the order of about 1.3 hours, if I remember correctly. So a little math intensive, but it was just a simple analysis of the system, defining a mass balance, defining each term that remained within the mass balance, combining, and then solving the integration. So if you want, you can just kind of circle the result and maybe keep that in the back pocket. In the event you see a tank draining type problem in quiz or exam, something like that. Are there any questions on how that expression was derived and how we could apply it to this tank draining system? All right, if not, we'll keep moving on, and we're going to talk next about an item known as Pitot tubes. Now, Pitot tubes are interesting because they can measure both static and dynamic pressures. Of fluid systems. And I'll describe what I mean by static and dynamic pressure. So if I've got fluid flowing through a pipeline, and I have two tubes that kind of jut out of this pipeline. The first tube just has a simple cutout where fluid can rise and fall to a certain height, each one. At the same time, I have a second tube whose inlet is within the flow field of the fluid, and it rises to a different height, H2. Now, if I were going to do Bernoulli balances on each of these systems, I would find some interesting information. Primarily, if we're looking at a balance on 1 and 2, assuming friction and work is negligible, I would say, well, for the intents and purposes, the velocity at the top of the tube is 0. The pressure at the top of the tube, if it's open to atmosphere, would be 0 gauge. The height of 2 is going to be that H1. The velocity at the entrance of the tube is going to be negligible, primarily because it's kind of at that entrance. The pressure of P1, well, it's going to have the pressure of the fluid within that pipe system. And if Z1's our reference, I can say Z1 is equal to 0. So what we're left with is an expression that says P1 over rho is equal to G times H1, which indicates that that first tube is primarily measuring the static pressure within the system, or H1, right? It's just simply following fluid statics. The height in that initial tube is going to rise and fall as a directly correlated or with the pressure of the fluid in the pipeline. Now the second fluid's a little different. If I look at a balance on 3 and 4, I can say, well, the velocity at 4 and the pressure at 4, I can neglect. So 0, this is going to be 0 gauge. The height at 4, well, that's that H2. The velocity at 3, now I can't neglect the velocity at 3 because it's in the flow field. The pressure at the 3 is also going to be the pressure of the fluid. And if I set my reference at Z3, I can neglect the height. And so what I'm left with is an expression that says G times Z4 equals U3 squared over 2. Sorry, this should be H2 because it's the second height I'm interested in, plus P3 over rho. Or H2 is equal to ChE Come on, gotta get my eraser to work. Or that height is giving me information on both the pressure and the velocity of the fluid. And so what this is a lot of times referred to as dynamic pressure, because it's not only looking at the pressure energy, but it's looking at a combination of the pressure energy and kinetic energy of the fluid. And so what you have is two different types of pitot tubes. One that's measuring simply the static pressure, or what we typically just call pressure of energy of the system. And the second tube is measuring the dynamic pressure, or the combination of both the pressure in the system as well as the velocity of the fluid in the flow system. So if the velocity of the fluid in the pipeline increases or decreases, H2 will rise and fall accordingly. However, H1 will not, provided that the pressure doesn't change appreciably without changes in velocity. And so this is the principle on how pitot tubes works in terms of looking at how it measures energy within fluids and how Bernoullis can describe those energy transfers within these types of devices. Now, I have a short video that I'd like to share with you of a more modern design of a pitot tube that's a lot more elegant, that further explains how these systems can work. So
Here is how
guys
this
hear the
measurement
sound okay?
method works. Pitot tubes have a rod-shaped measuring element that is inserted into the pipeline perpendicular to the flow direction. On the front and rear of this probe are several holes. Two separate tubes connect these holes to a differential pressure sensor. With its two pressure chambers, separated by a diaphragm, the tiniest pressure differences in the flowing fluid can be precisely measured. The individual pressure taps are distributed along the entire pipe cross-section to ensure a representative measurement. If there is strong interference in the flow profiles, it's advisable to fit a second pitot tube, rotated by 90 degrees.
Oh no, it stopped. I apologize. Are you guys at least able to see and hear the video okay?
flowing. As soon as the fluid starts to flow, an additional impact pressure against the front of the probe is generated, also known as the dynamic pressure. On the rear of the probe, in contrast, only the static pressure, which is not related to the flow, is still measured. As a result, different values are detected in the pressure chambers of the sensor. Higher pressure against the flow and constant pressure on the rear of the pitot tube. This pressure difference is a direct measure for the flow velocity and thus the mass and volume flow in the pipe. The higher the flow velocity and therefore the dynamic pressure, the greater the differential pressure measured. Pitot tubes are able to register the flow in both flow directions. This means that balancing measurements, for example in gas pipeline networks, can be carried out at any time.
All right. I just thought that was a good way to see a more modern design based off these principles. Any questions on how pitot tubes work? All right. So then what I'm going to do next is we're going to start looking at an example on the use of pitot tubes where we can calculate the velocity of water flowing through a pipe if a pitot tube is installed and shows a height of 2 feet. So a tube that's measuring the dynamic pressure, and then a static tube is also installed that shows a height of 8 inches, which is simply measuring the static pressure. So what I'm going to do is I'm going to throw you guys in breakout rooms. So work for a few minutes together in small groups and see if you can come up with the velocity of the fluid from these measurements in these two tubes. All right, so what did you guys come up with for your velocities?
I got 9.3 feet per second.
All right, that's great. That is correct. Did the other groups get something similar as well? Or did you guys get some different values? One way to look at this problem is I kind of, from our little exploration earlier where we had expressions for the height 1 and height 2, if I rearrange them a little bit, I can get my height 1 equaling to the pressure, the height 2 equaling to both the kinetic energy and the pressure. So if I combine these two expressions, what I can be left with is H2 is equal to U3 squared over 2G plus H1, which means I have H2 minus H1 is equal to U3 squared over 2 times gravity, which simply means if I'm going to solve for that velocity, all I need is an expression that looks a lot like the tank draining system. So just looking at the difference between the heights and plugging into this expression, I can directly solve out for that velocity, which should be about 9.3.
Are you writing
Are you
on a
drawing? 'Cause
whiteboard?
Yeah, I'm sorry. I forget that I have to keep switching. All right, so I'll step back. So this looking like at the example of static tube measuring 8 inches, excuse me, and the dynamic tube measuring 2 feet. So rearranging the initial expression for the static tube, I have that first height is equal to the pressure energy, the second height equal to the sum of the pressure and the kinetic energy. Combining these expressions, I can get essentially an expression of the second height as a function of the first height and the kinetic energy, and then rearranging, I get this final expression that looks a lot like the tank draining equation. Or if I just look at the difference in the heights, I can quickly calculate the velocity of the fluid. Any questions on that example? Well done. The next thing I'd like to talk about is fluid head. Now, if I write my mechanical energy balance, and I can write it like this for a reason. I have an expression like this. And what are the units of each term in my mechanical energy balance?
Is that
Meters.
Well,
So I have what? I'm sorry, I had two people talking.
I asked, was that delta P over rho?
Yes, change in pressure over density.
Meters squared per second squared.
Yeah, so meter squared per second squared, or length squared per time squared. So while kind of nice, it's not really helpful. But if I take every term and divide by gravity, I get an expression that looks like this. Very similar, but a little different. However, the implications are fairly important. Now, what are the units in each of these? Which I denote by an equal sign in brackets for units. Now the units is simply length. By dividing essentially by meters per second squared, I'm just left with meters or length. And when I define my energy balance in these terms, every term, for lack of a better word, in this expression is now defined as a function of just a simple length. And what we call this is defining our energy in terms of what's known as head or fluid head. And so my kinetic energy becomes my velocity head. My pressure energy becomes my pressure head. My static energy, just my static head. My work is simply head added, which I'll explain here in a second. And my friction over gravity is head loss. And a lot of times, the final two expressions are written a little differently, and I'll explain why. So if I'm looking at the simplified energy balance, or the simplified Bernoulli, I can write my expression like this, correct? P2 over rho, G times Z2 equals U1 squared over 2 plus P2 over P1 over rho plus G times Z1. Now, if I write this in terms of head, I just change where gravity shows up in the expression. But what I'm left with is essentially something that looks like this. H1 is equal to H2, which means the total head in the system at point 1 is equal to the total head in the system at point 2, or my delta H, or my change in head, is equal to 0. So in a simplified system, the fluid head does not change. In a true mechanical balance system, my change in head is simply a function of work over gravity plus friction over gravity, which a lot of times we write this second term as H sub L, or head loss, which means the delta H, which is looking at the kinetic pressure and static energy, can be wrapped up in terms of just what's the head of my fluid at these points. Well, it's either conserved or a function of what's happening with work, which we're typically adding, or the head loss of the system. And this it's a little, it can be considered a little odd. However, a lot of times when describing energy within a fluid in terms of head, it's done in a way to make the expressions a lot more straightforward. Typically, because when you're looking for power requirements or energy requirements for a fluid system, a lot of times it can be done in an expression of, how much head is necessary to be added to get fluid from point A to point B. And I say that because when we start talking about metering and equipment, particularly pumps and compressors, a lot of the figures and curves that we use to describe those are done as a function of head added, or delta H, versus our desired flow rate. And so it's another way of looking at our energy balance in just a little way that makes some of the discussion and data presentation a little neater. And it's just, it's also one of those things that's just, this is how a lot of things are described when it comes to fluid transfer equipment. So instead of saying, this system needs, 35 joules, a lot of times you'll say, well, this, if I got a flow rate of 10 liters per second, we're going to need 18 meters of head added to the system. Is there any questions or things I can further clarify in terms of how manipulation of the energy balance gives rise to the terms described as fluid head, as well as why that's necessary in certain situations? All right, so let's look at an example of doing some calculations with fluid head. So if I have a pump storage facility that takes water from a river at night and pumps it to a hilltop reservoir 300 feet above the river, the water is returned during the daytime to help meet peak energy demand. So assuming we have a 20-inch pipe 1,500 feet long, what pumping power would be required if the pump would move 80 gallons per minute? So this is kind of going to be a little crazy in terms of the calculations. So let's take a look at this one. So we've got a hilltop reservoir, 300 feet up. Our pipe diameter is 20 inches. Pipe length is 1,500 feet. And we're looking for the power requirements, assuming our volumetric flow rate is 80 gallons per minute, which should be approximately about 0.178 cubic feet per second, which is quite a lot of fluid. So let's take a look at the system together. And we can look at this in terms of fluid head. I'll just call it head loss. I just like writing it that way. So in this system, we can say the head to be added, or a lot of times I'll write this as delta H, is equal to delta U squared over 2G plus delta P over rho G plus delta Z plus H loss. Now, for now, we're just going to neglect friction. And we have to ask ourselves, which of these values can we neglect? Well, if I'm not worried about supplying pressure, I can assume my start and end points are going to have the same pressure. In this system, I can say, well, I have U2, it's going to have some velocity, and U1 is going to be negligible if I pick the points like I typically do. And so what I'm left with is to apply my system, I have to input some form of kinetic energy, and I have to deal with the static energy requirements. So what I need to find is my flow velocity, because I know that my delta Z requirements is 300 feet. And so my velocity is going to just be my flow rate over my flow area, or my 0.178 cubic feet per second divided by pi times 20 inches, which is 1.67 feet squared divided by 4. Which, if I do this math, what do I get for my flow velocity? I'm getting something fairly low.
I got 0.081 feet per second.
Yes, that's what I got too. Sorry, I was having a little trouble with my calculator. It's pretty low, which means all the energy we're going to be adding is mainly going to be in that static energy. So our delta H we're looking at is 0.081 feet per second divided by 2 times gravity, or 32.2 feet per second squared, plus 300 feet. So if I take our velocity and I square it, I get something really small, such that the delta H is pretty much going to be that 300 feet. So now we know our work requirements. We can solve for our power, which I don't know if I said anything about efficiency. So what would you guys like the pump efficiency to be?
90%.
90%. All right, I like it. So we're going to assume eta is 0.9. So I have 62.4 pound mass per cubic feet times our flow rate, which we had, which was 0.178 cubic feet per second, times our work, which was 300 feet, divided by 0.9. One thing we have to be careful with when you're looking at this is our units. Since I'm dealing with fluid head instead of just the regular work, I have to check my units. So what we have here is, this gives us what? Pound mass feet per second. But we need it in pound force feet per second. So to do the conversion, what we need to do is multiply times gravity and divide by G sub C. So if we multiply times gravity and divide by G sub C, so I get 32.2 feet per second squared divided by 32.2 pound mass feet per pound force second squared. I can check my units. And now We have the pound mass going away. This cubic feet goes away. One of these feet goes away. The seconds squared goes away. Now I have pound force, foot-pound force per second. And then I can do my conversion, which is 550 foot-pound force per second is equal to 1 horsepower. So I end up with about 6.7 horsepower. So one thing you note, well, it's kind of silly that we did this G and G sub C, right? Because I'm essentially multiplying by unity to deal with my units. And so what that tells you is when you solve for work in terms of head, what you're left with is foot-pound mass per second. And for intents and purposes in these types of problems, pound mass and pound force, when you're dealing with head, you'll find that when you have to multiply times G sub C, the values are going to be the same. And so it's just something to keep in mind when you're doing these calculations. Are there any questions on that? If not, I think that's a good stopping point. So it looks like we won't be able to jump into momentum balances until Friday. So one thing I will do, I'll send an email right after class. I'm going to go ahead and push back the homework due date, probably till Sunday night, just to give you guys a few days to finish up the 2 problems on the homework set, since we haven't really, quote unquote, talked about it yet. So give me about 10 minutes and I'll send that out. Are there any last minute burning questions? If not, thank you all for attending class. I hope you guys have a great day. And if you have questions, feel free to stop by office hours or send me emails.
Thank you, Dr. Lopez. Bye.
No problem. You're welcome, Aaron. Take
Thank
care,
you.
guys.
Lopez.
Have a great day.
You too.